Hi, welcome back. If you haven't already done so, please go back and watch the introductory videos in the series that introduce the basic concepts behind graphs. In this video, we will dive right in to learn how to model graphs in Kinetica using the two components of edges and weights. Let's start by looking at the four different components that can be used to model graphs in Kinetica. The first component is an edge. Edges represent relationships. An edge can also have an optional direction that specifies the direction of traversal. For instance, think of one-way versus two-way roads. The next component is the weight associated with each edge. We can use weights to assign costs for traversing the edge. These are useful when solving a graph. Next, we have nodes that represent different entities in a graph. Think places, people, objects, etc. The last component are restrictions that can be used to block access to a particular node or edge while traversing a graph. The primary goal when modeling graph data is to reliably identify these components from your data to build a graph. Let's look at a sample table with geographic data to see how we might go about doing this. The bare minimum requirement for building a graph is to be able to identify edges. Consider this table with just a WKT column that contains line strings. WKT, or well-known text, is just a common markup language that is used to represent geospatial data. Each row here corresponds to an edge in a graph. We can use this to create an undirected graph where the nodes are implicitly defined at the intersection of edges. The weights for these edges are undefined at the moment, and there are no restrictions on the edges or nodes. Let's add some direction to this graph. In this new table, we have a direction column. Directions are set using an integer column that can take three possible values. 0, which allows traversal from the starting node to the end node for an edge. 1, which indicates a two-way edge that can be traversed in both directions. And 2, which indicates an edge that can only be traversed from the end node to the starting node. The corresponding graph can be represented as follows, with arrows indicating the allowed directions of traversal. Notice that the edge with the direction value of 1 is marked as a two-way edge, implying you can traverse this edge in both directions. This illustration represents a directed graph with nodes that are implicitly defined at the intersection of edges. This graph has no weights or restrictions assigned yet. Now let's say we wanted to find the best way to get from the leftmost to the rightmost point in this graph. We have two options. Path 1 is the red colored route while path 2 is the green route. But which one is better? This is where weights come in. Weights typically represent the cost of traversing a particular edge. For instance, think of say the condition of a road, the speed limit, etc. They can be added either when creating a graph like we are doing right now, or separately at the time of solving. We can denote weights using numbers that are placed next to the corresponding edges. Now using this, we can see that the best way to get from the leftmost point to the rightmost point is the first path that has a combined weight of 20. However, right now the edges are identified solely using the WKT strings. While this works, it is not easy to represent paths in a human-readable way. Let's add some edge IDs to make this easier. Now we can represent the best path using the IDs as follows. Edge IDs 1 and 2 with weight 5 and the ID 4 with weight 10 with a combined weight of 20. So far, we have looked at a rather simple illustration of graphs where two nodes are connected by a single edge. In the real world, we have cases where there are multiple edges between the same two nodes that have different weights associated with them. For instance, think of a multi-lane highway where each lane in the highway has different speeds of travel. Kinetica's Graph API can be used to model such complex scenarios as well. Let's say for instance that the edge 3 in our current table has two additional lanes with the costs of 25 and 5. The table now will look like this. In this case, since the lanes are adjacent, we can assume that they can be represented geospatially using the same WKT line. However, we can distinguish one from the other using different edge IDs. Each of these edges can now have different weights, perhaps indicating the speed of travel, the quality of the road, high occupancy lanes, etc. We can depict this graph as follows. Notice the 3 edges with the 3 different weights that replace the earlier single edge. Now if we were to try to solve this graph for the same 2 nodes as before, we would get a different path. Instead of going via the first path, we now go through the second path using the faster edge with cost 5. This path can be represented as follows, and it has a total weight of 15, which is lower than the previous total of 20. So in this video, we learned how to model graphs in Kinetica. At the bare minimum, to create a graph in Kinetica, all you need is information about edges. These edges can be directed or undirected. We can model additional information about the costs of traversing these edges using weights. Finally, Kinetica's Graph API also allows us to model complex scenarios like a multi-lane highway using additional edges which are distinguished from each other by their IDs.